Okay, good evening, everyone. This
Good
is
evening, sir.
lecture series on electronic components. Today, we shall be dealing with resistors. Let me quickly share my screen. Please confirm you can see my screen.
Yes, I can see you, sir.
Okay. So the other time, on module 2, we talked about resistors. Today we are dealing with capacitor. Let me quickly say this, and it's important to take note of what I'm about to say. If you want to develop, if anybody wants to develop an expertise in electronic designs, you have to study in details diodes, resistor, capacitor, inductor, transistor. You have to study in details diodes. What I mean by diodes have their category. Diodes have their categories. You have normal diode, you have Zener diode, you have LED, and the other ones. When you come to resistor, you have different types. When it comes to inductor, you study it in details. Capacitor, you study it in details. Then inductor, you study inductors in details. If you can study these things in details, you will be able to understand every other thing about electronics because every other thing revolves around these components. For example, if you pick up a transformer, it's application of inductor. If you pick up a typical IC, you are dealing with resistors and capacitors and transistors. Anybody that understands transistor, capacitor, and resistor will be able to understand operational amplifiers and their modes. And what I mean by studying this in details, I don't mean just reading about them. You have to spend some money, get these components, set up a small lab. Electronics can be practiced in a room. Get oscilloscope, get function generator, get power supply, get your multimeter, get your breadboard, get your jumper wires. Begin to experiment on these things so that the knowledge will not be theoretical. Once somebody masters this basic stuff, there is no electronic design you will not be able to understand. In fact, you become a good designer. Because even sensors, you notice that sensors, they are just application of these components. Optocouplers, the same thing. If you open up an optocoupler, for example, what you will see there is a diode and a transistor. You pick up a triac, you notice it's the same thing. You just see the symbol of two diodes there. So you pick up any sensor, for example, thermistor, it's all about resistance. This time around, temperature dependent resistor. So this is actually the key. That's why I'm trying to devote time to see if we can cover these components in details within this period. And then I will leave you with that. Today we are looking at capacitor. This is the symbol of capacitor. This is non-polarized capacitor, polarized capacitor, variable capacitor. And then we are going to look at capacitor definition and types. And that's what we're going to do today. We will not be able to cover basic functions of a capacitor in an electronic circuit. Capacitor is a bit wide. Then understanding of mathematical model of a capacitor will help somebody to appreciate the function of a capacitor both in AC and DC circuit. Then voltage frequency response of a capacitor will help us see that at high frequency, the impedance of capacitor will reduce. But at low frequency, the reactive impedance, that is the reactance, will increase. These are concepts that will help one to understand how these things are applied in electronic circuits. At low frequency, capacitors and inductors behave differently. At high frequency, when it goes to telecommunication level, they begin to behave differently. That's why telecommunication is a specific domain, because once the frequency is high, capacitor and the inductor behavior change, or that it changes. So we move capacitor definition and types. A capacitor is a passive electronic component that stores electrical energy temporarily in an electric field, consisting of two conductive plates separated by an insulating material. That insulating material is called dielectric. Capacitor basically blocks direct current. We're going to see that later, while allowing alternating current AC to pass. So anyone that has understanding, not just theoretical understanding, mathematical understanding of this, once you see a capacitor in a circuit, you should be able to have a rough idea of what it's doing there. Talking about dielectric, or the construction of a capacitor, so look at this figure where my mouse is pointing. You see two metal plates. In between them is an insulator called dielectric. So once these two terminals are connected to voltage, this is source, this stores energy. The dielectric stores energy. This is the normal capacitor we see. The normal capacitor, this one is common everywhere. So you can see that we have anode, cathode, and then this is the packaging. Okay. There is another kind of capacitor. This is a very big capacitor, the one you normally have in your sumo water pumping machine. This is the kind of capacitor, or even in your generator. This is the capacitor you see there. Please, who is using board now? Who is using whiteboard? Who is using whiteboard? You know this documentation is being recorded. Okay. So now we have inside of a ceramic capacitor. This is what you see inside. You see the electrode, the protective coating, see the dielectric. The principle of construction is the same. What changes basically is dielectric, which is the insulation material. We move to the next slide. Capacitor has two conductive plates separated by an insulating material called dielectric. I've said it before. It's the same thing. What we are trying to do is to show the picture in different forms for visual understanding. You see the same thing here. This is the dielectric. This is a typical capacitor when it is not connected to power. Capacitor blocks DC and allows AC to pass. Just to confirm that you are still with me, can somebody read this equation?
Um,
Let
XC is
someone
equals
read
to
this
1 over,
equation.
okay, I said XC is equal to 1 over WC is equal to 1 over 2 times PI times F times C.
Okay, so that is the basic equation of basic mathematical model of reactive impedance of a capacitor. So from that point, we can see that as the frequency increases, the reactive impedance begins to decrease. It simply means that at a very high frequency, the reactive impedance becomes zero. So it's as good as that capacitor is no longer there. It becomes a shunt. To just diminish to zero. At a very low frequency, the impedance will be very high. Now, when the frequency is zero, before we go proceed, just look at this. I like everything I do. I like making it practical. This is MATLAB environment. We are not teaching MATLAB, but let's say that XC, we see that XC is equal to 1 all over 2 pi F 2 pi star F star C.
Sir, we are not seeing anything, sir. Is it intentional, sir?
You're not seeing anything?
No, sir. I'm just seeing your video. I'm not seeing what you are typing, sir.
Oh,
Yes, sir.
okay.
Nothing is showing.
Can you see my screen now?
Yes, sir. Yes, sir. It's back.
Okay. So I want to plot the graph of reactive impedance of a capacitor versus frequency on MATLAB environment so that you have a visual understanding of what I mean. So let's say we have C to be equal to 1000 microfarad, which is equal to 1000 times 10 raised to power minus 6. That's 1000 microfarad. So we suppress it, or if we enter it, to just give us the value of C. Now, that's correct. Times 10 raised to power minus 6, 1000 times. Okay, so we have, let's say that our F, let's begin from 0 up to, let's increase it by, at increment of 100, let's get up to um 1 megahertz, 1 megahertz, that is this, we suppress it. If we don't suppress it, it will be too much when it displays. So, and now we have that XC is equal to 1 divided by 2 times, this is dot multiplication, 2 times what? 2 times pi, and times again, times what? Times f, and then times c. Again, we suppress it. Now, where is the error coming from? 1 divided by 2 times pi times x is 1 over 2 dot pi dot f, that is f, dot c. Why is it okay, okay. I think I've seen the problem. Need to shift this. Want to shift this. It will be here so I can see. Oh, please, who is using whiteboard now? Why is my distance changing to what I don't understand? Okay, I think I'm supposed to, this is supposed to be dot division as well. So let's check again. So that's XC. We now say plot, we are plotting XC against F. So let F be on the horizontal and XC be on the vertical. And then we plot it. We wait for the graph to come up. I don't know whether you can see this. I don't know whether you can see this. Whether you can actually see this graph. Look at the way, let me see. Let me change this range. Probably we'll take a small range so that we take a small range, 0.5, and let's leave this one at 20. So let's see how it will help us. And then this thing is disturbing me. Okay. And we execute this again. Let's see whether it will. Good. So this is our graph. We call here, this is frequency, um, and this is XC, and this is we can name it anything, plot of XC versus pre frequency, and then we can increase this one to make it look better. So this is the plot of reactive impedance versus frequency. We can see that as the frequency increases, what happens? What happens? Nobody is talking. Please confirm you can still hear me.
Yes, yes, sir. I can hear you, sir.
Well, we all did fundamental physics now. This is graph of impedance versus frequency. So as the frequency is increasing, what happens to impedance?
I think it reduces.
Impedance tends towards zero. When for example, when the frequency is zero, you notice that at this point, impedance tends towards infinity. But as the frequency of the signal begins to increase, the reactive impedance begins to decrease. These are the mathematical realities anyone that wants to function in the domain of engineering should know. At least should be able to look at an equation and state the limits at so and so condition. So that's that. We can now see, if we now look at this equation again, based on this equation, you will now notice that when the frequency is zero, reactive impedance will be infinity. It will be infinite. And then it will block DC because the frequency of a DC signal is zero. Okay? If the frequency begins to increase, this guy, XC, begins to decrease. And then you can begin to understand that capacitor can be used for low pass filters. It will simply pass signal that of low frequency. When the frequency increases, that same capacitor will begin to function as a shunt, sinking back the high frequency component back to the source. These are not the things you cram. These are the things you know by understanding. Let's simulate these two circuits so that we can see what it's all about. I mean, when we say that capacitor blocks AC, I mean blocks DC. You can still see my screen.
Yes, sir.
Okay. So this circuit now, this is 220. I left it at 1 Hz so that we can see what is going on. The normal frequency of AC here is 50. This is a capacitor, electrolytic capacitor, 1000 microfarad. And then this is a resistor connected in series with an LED. We've discussed LED before. And this is a AC voltmeter. This is DC voltmeter. This one is a DC. This one is AC source. This one is a DC source of 12 volts. The same capacitor, AC voltage, DC voltage. The only thing that changes here or that changed here is just the source. We run it, we simulate it. You notice that this one is blinking at the rate of 1 Hertz. At the rate of 1 Hertz, that is 1 second, 1 second. Now, the meters are reading, but here, what do you observe here? What is this one reading?
The other
Please,
one is
I
not
need
reading.
I
It's
need
not
your
reading.
response. The voltmeter
One
here,
is not reading.
what is what is the value there?
It's 0.0. It's not reading.
0.
Eh?
Okay. Oh,
0. That one
I
is not
think
reading.
It's not it's reading
this
0.0,
other
meaning
one.
that confirming that this capacitor has blocked the flow of current because this is DC. If you doubt it, just remove the capacitor. It's the capacitor that is the problem. Run it again. You see that? So these are the things we need to take note of. Capacitor blocks DC, allows AC to pass. That is the basic about capacitor. Anywhere you see it, especially when it is connected in series with the source, or in any amp where a capacitor is a kind of connected in series, just know that it's being used as a coupling capacitor, meaning that the designer wants only AC to pass through that point. Any component of DC must be blocked. Okay? So we proceed then with our presentation. Are we together? Are we on the same page?
Yes, sir.
I just hope the network will continue to be fine. The
Yes, sir.
rain is starting here. Now, dielectric materials using capacitors. Dielectric materials are essentially insulators, which means that no current will flow through the material when a voltage is applied. However, certain changes do happen at the atomic scale. When a voltage is applied across a dielectric object, it becomes polarized. Since atoms are made of a positively charged nucleus and negatively charged electrons, polarization is an effect which slightly shifts electrons towards the positive voltage. They do not travel far enough to create a current flow through the material. The shift is microscopic but has a very important effect, especially when dealing with capacitors. Once the voltage source is removed from the material, it either returns to its original non-polarized state or stays polarized if the molecular bond in the material are weak. the difference between the terms dielectric and insulator is not very well defined. All dielectric materials are insulators, but a good dielectric is one which easily polarized. So this material don't conduct totally, but they are polarized once electromagnetic field and once a charge is brought between the terminals. So that's what brings about the capacitor. Once it's polarized and you remove the voltage that charges, the charge remains. And that's the principle of operation of a capacitor. Common dielectric materials, you have ceramic. In fact, most times capacitor is named after the kind of dielectric material that is used in constructing it. You have ceramics, known for high dielectric constants. You have beryllium titanate. You have titanium oxide. You have silica. These are dielectrics. And then you have plastic. You have electrolytic. All these things. When you get the lecture materials, you go through them in detail. All these have different dielectric constants as we are going to see. We're still on common dielectric materials. You have paper, frequently impregnated with oil or epoxy for high voltage and AC applications. You have mica, known for excellent stability and high frequency performances. You have conjugated polymers, and then key characteristics of dielectric materials. You have dielectric constant K or epsilon R, and what it means that if a material has high dielectric constant, it means it can store more energy. Okay? Dielectric strength measures the maximum electric field a material can withstand before breaking down and becoming conductive. As you may be aware, if a capacitor is rated 25 volts, you don't supply close to 25 volts. You don't supply 25 volts. You don't connect it across 25 volts. It's likely to break down. If you know that the voltage point is 25 volts, then go for 35 volt capacitor. That is a rule of thumb. Temperature stability tells us how much dielectric constant changes with temperature. Okay, then you also have dielectric loss, which measures efficiency. Loss is critical for high frequency applications. Then we come to dielectric constant. Remember I said if you want to understand the electronics, you have to study things in details. One of the things of the rise in our generation is that people don't want to study things in details. Very few people care about studying things in details. We see it in the day-to-day life of our students. All they want is this quick stuff. And then the challenge is that when you now want that person to design something meaningful, that person will not be able to do it because that thing, the person doesn't know it in details. The person just read it at a very peripheral level. Nobody produces anything with peripheral knowledge. Anybody that knows something at very peripheral knowledge will not be able to come up with any product. Okay? So the dielectric constants of a material, also called the permittivity of a material, represent the ability of material to concentrate electrostatic lines of flux. In more practical terms, it represents the ability of a material to store electrical energy in the presence of an electric field. All materials, including air, what we mean by vacuum here, we mean air, including vacuum or air, or when there is no air, store energy when placed in an electric field. The permittivity of vacuum is defined as the physical constant epsilon 0. which is approximately 8.854 times 10 raised to the power minus farad per meter. That is, yeah. This constant appears in many electromagnetism formulas. Since most capacitors are not made of vacuum, it makes sense to define permittivity for every material. The permittivity of a material is defined as epsilon is equal to epsilon r multiplied by epsilon 0, where E is the absolute permittivity and epsilon r is the relative permittivity. Epsilon r is a number which is always greater than 1, meaning that all materials store more energy than free space when subjected to an electric field. This property is quite useful in capacitor applications. It should be noted that the relative permittivity depends on many factors such as temperature, pressure, and even frequency. And that is why materials with more stable dielectric constants are favored in some applications. So the next table, the table we are going to see, gives us some materials and their dielectric constants. You can see the material with vacuum has 1, water has 30 to 88, and glass has 3.7 to 10, etc., etc., etc. When you get the lecture material, please go through them. This forms the theoretical background upon which you are going to build your practical knowledge. Dielectric strength, I've talked about it before. Unfortunately, there is a limit on the voltage an insulator can withstand before conducting electricity. All materials have an upper voltage limit called breakdown voltage. A good example of this is A. It is considered an insulator, but under certain circumstances, it can flow current. This is exactly what happened during the lightning strike. After the breakdown field strength is exceeded, A is ionized, electrons are turned away from atom's nucleus. Also, in high voltage transformers, you don't need to touch any wire there for you to be electrocuted. If you go close to high voltage transformer, literally, you will be drawn to the transformer. Why? The air has been turned to conductor. So that is that. So we are saying that when A is ionized and they begin moving under the influence of electric field, producing electric current, it is very important not to exceed the maximum rated voltage of a capacitor in order to prevent damage or even complete destruction. I've said it before. So let's continue. Dielectric loss. The term dielectric loss refers to the energy that is run to heating of an object that is made of dielectric material if a variable voltage is applied to it. We move on. The formula C, epsilon r multiplied by epsilon 0 multiplied by A over D, is used to calculate the capacitance of a capacitor, parallel plate capacitor. C is the capacitance, E, R is the relative permittivity. So this is the formula, the theoretical formula for calculation of capacitance of a capacitor. Yeah. Let's go to capacitor types. Number 1, fixed capacitors. Fixed capacitors, which are in categories. Number 1 on the list is ceramic capacitors. The most common type, utilizing ceramic as a dielectric. They are inexpensive. These capacitors, especially this one, with 100 naira you can buy it. Some even 50 naira you can buy it. They are inexpensive and suitable for high frequency application, though they have low capacitance. How do you calculate them? You will normally have a 3-digit or 2-digit written on them. For example, you may have 104. The first two numbers are digits, while the third one is a multiplier, and they're always rated in picofarad. Picofarad, for example, 104 means 10 times 10 to the power 4 picofarad. It's raining heavily here. Please, can you still hear me?
I can hear you, sir.
Okay.
I can hear you, sir.
Steps to calculating ceramic capacitor value. 1. Identify the code. Locate the 2 or 3 digit number on the capacitor body. And then the significant digits, take the first 2 digits as the base number and apply the multiplier. So you can see here, 223 means 22 times 10 raised to the power 3 picofarad. They are always rated in picofarad. And the common ones, you have 101, 104. Some of these vendors, that is what they understand. Tell them ceramic. Say you want to buy capacitor, they will ask you which number. You mention the number. Okay, they will first of all ask you which type. Is this electrolytic or ceramic or titanium? They begin to mention this. And then if you say it's ceramic, they ask you which number. You have to mention the number. And then when you do your calculation, you notice that 104 is 0.1 microfarad, while 103 is 10 nanofarad, while 474 is 0.47 microfarad. You also have the numbers written, alphabets written on the ceramic capacitor. You have J, you have K, you have M. These represent the what do you call it again? The tolerance. The tolerance is similar to what we discussed in resistor. The tolerance. So J represents 5% tolerance, plus or minus. K, 10 plus or minus tolerance, while M is plus or minus 20% tolerance. We'll move over to electrolytic capacitors. They provide high capacitance values, making them ideal for power supply circuits and low frequency application. And within the family of electrolytic capacitors, you have aluminum electrolytic capacitor, you have tantalum electrolytic capacitor, you have polymer capacitors. This is what I mean. Aluminum electrolytic capacitor, you can see them, they are common. Okay, how to know their polarity is very simple. Just look at the body. You will see a negative distance. Just know that one is negative. Also, most of the times, especially this type, where's my mouse? Especially this type, the positive side always have the longer leg. For this type, you need to look at the body to know which side is negative and which side is positive. You also have tantalum electrolytic. Tantalum electrolytic capacitors are highly polarized, compact, passive components known for high capacitance per volume, stable performance, and high reliability. They use tantalum metal as anode, forming a thin dielectric oxide layer, making them ideal for space-constrained applications like computers, telecommunications, and aerospace. So you see, it's not one type. You have to know what you really want and the type of capacitor you need. Within the value of a tantalum electrolytic capacitor involves identifying the capacitance, which can either be in farad or picofarad, the voltage rating, and the positive polarity terminal. It's always written on the body. Unlike aluminum electrolytic capacitors, which mark the negative side. Tantalum capacitors typically mark the positive side with a stripe or a cross sign. You can see that. We move. The next type of electrolytic capacitor is polymer capacitors. You use a solid polymer electrolyte for lower equivalent series resistance and longer life. Polymer capacitors or polymer electrolytic capacitors are high-performance components using solid conductive polymers as electrolytes, offering exceptionally low ESR, high ripple current capability, and long lifespan. Ideal for power management in servers, computing, and industrial electronics. They provide stable capacity at high temperatures and frequencies. Reading the value of a polymer capacitor is usually straightforward, as they often have their specification printed directly on the body. You can see that. This is 470 microfarad by 16 volt polymer capacitor. And then the next type of a capacitor is film capacitor. Film capacitors are highly reliable, non-polarized capacitor using thin plastic films as dielectrics, commonly found in power electronics, automotive, that's electric vehicles, and industrial applications. Known for self-healing capabilities, low ESR, and stable capacity across temperatures. They excel in EMI filtering, DC link, and high-frequency pulse applications. How to read this is still the same thing, the way we read ceramic. Like this is 222 times 10 to the power 5 picofarad capacitor, 400 volts. There you find out they should represent the tolerance. And then we have supercapacitors. Supercapacitors are high capacity energy storage devices that bridge the gap between conventional capacitors and batteries. They charge very fast. They charge very fast. They provide unparalleled power density, allowing for near instantaneous charging and hundreds of thousands of cycles, though with significantly low energy density than lithium-ion batteries. Ideal for rapid energy storage, they excel in applications like regenerative braking and quick large electronics. Okay, these are employed in electric vehicles. So, the key characteristics and benefits: rapid charging and discharging. So they can charge devices in seconds or minutes. Long lifespan, withstand hundreds of thousands of cycles without significant degradation. High power density, deliver large amounts of power quickly. Low energy density, store roughly less energy than lithium-ion batteries. Low voltage, they normally operate at low voltages, 2.3 to 3.3. If you want to get a high voltage from them, you have to cascade them. Okay, connect them in series now. This series now parallel. When you connect in parallel, you have the same voltage in series. Then you have silver mica capacitors. Silver mica capacitors are high precision, high stable, and reliable capacitors characterized by using mica as a dielectric, often found in low value radio frequency and high frequency applications. These capacitors offer low losses and exceptional stability over time and temperature. So anytime from today you open electronics, you'll be able to identify stuff there. You open up any electronics, you notice that what you are going to see there, if it is not diode, it belongs to, if it's not one form of diode, it will be one form of capacitor. If it's not one form of capacitor, maybe one form of inductor. If it is not one form of inductor, maybe one form of resistor. If it's not one form of resistor, it may just be a transformer. If it's not a transformer, it may be a transistor. If it's not a transistor, it might be a MOSFET, which is also a family of transistor, or it's an IC. But if you don't study this thing by just opening a circuit, you study them one by one at component level. We come to variable capacitors. Variable capacitors, among them, number one is trimmer capacitors used for initial calibration or tuning of electronic circuits. So you can see them just like they look like variable resistor, which you can actually tune. So unlike user-adjusted variable capacitors, these are set once with a screwdriver and used to adjust radio frequencies, oscillator frequencies, and signal latency. You now have variable capacitors. Okay, the trimmer capacitors, the key characteristics, they are applied primarily in radio frequency circuits, filters, and oscillators. Adjustments more often featuring a screwdriver slot designed for precision rather than frequent adjustment. Balancing types, commonly ceramic, air, or glass. So, and then the capacitance can range from few picofarad to about 100 picofarad. They are non-polarized. Common uses, calibration, easy to set calibration, calibrate equipment, and then radio frequency matching, that's impedance matching. We need to take note that the capacitor, this type of capacitor is almost they are becoming obsolete because of improvements in technology. So, but there are still some equipment that use them. Finally, on capacitors, we have tuning capacitors. Tuning capacitors are variable capacitors used to adjust the resonant frequency in radio receivers, oscillators, and the filters. So definitely this is an industrial, or these are industrial capacitors. They function by altering the capacitance, usually by shifting the overlapping area of rotor and stator plates to select specific radio stations or frequencies. I need to say that some of these things are automated now. So the selection will be automatic. So this is the end of today's lecture. Thank you for listening. I don't know whether anybody has any comment or question or contribution.
Hello, sir.
I can hear you.
Okay, sir. Yes, I want to ask, sir. Sir, you made mention of low frequency, high frequency.
I'm not hearing you clearly. Is there a way you can amplify your voice?
Oh, okay. Is it better now? Can you hear me now, sir?
But it's still down. Let me see. Oh, yeah, talk. Let me see.
Can you hear me now, sir?
Yeah.
Okay, sir. Sir, you made mention of capacitors also assisting in low frequencies and high frequencies.
Yes.
These low frequencies and high frequencies, these terminologies, is it with respect to what do you mean? Is it with respect to sound, or there's other thing being defined as low frequency or high frequency, sir?
Yes. There are applications that need frequency bands We call it band pass filters. There are applications that need band pass filters. You want frequency at so and so range. You at lower frequency, you want to cut it off. At higher frequency, you want to cut it off. What you use to design such band pass filters is actually a combination of resistor, capacitor, and inductor. Look at what I mean. You are see. Let me share my screen.
Monday to Saturday. Pastor,
can you see my screen?
Yes, sir, I can see, sir.
So let's type band pass filters. You check for the image, the schematic. What do you see here?
I'm seeing a diagram. Band pass filter.
I'm opening it up so that it will become obvious.
Okay,
I
sir.
want it to be bigger. So, what do you see here?
I'm seeing the diagram. Completed band pass filter circuit.
Okay. This one is high pass filter stage, low pass filter stage. You notice this is a capacitor. This is a capacitor. Now let's consider this. Let's consider this. High pass. High pass means it's going to pass high frequency and stop low frequency. You notice that XC, reactive impedance of
Okay,
the
sir.
capacitor, is 1 over WC. So at low frequency, this reactive impedance will be high. It will block it. But at high frequency, this capacitor here will almost act like a normal wire, just a conductor. So high frequency signal will pass. Now coming to this point, what happens here? At high frequency, this one will act as a shunt. So some high frequency component that is not needed will sink. So why is it? High frequency will pass here. Coming to this point, some of them that is not needed will go back to the source. It's now left for you to define your frequency. This is the frequency I want. This is frequency I want. But for sure, this is the architecture of your bandpass filters. Is when you now understand this, you now begin to talk about what is the formula for the signal coming to this point and signal coming to this point. But at this level, you need basic understanding, at least when you see this circuit, without thinking, without too much analysis, you should be able to say that this is what this circuit is doing. I don't know whether that answers your question.
Yes, I get you, sir.
Okay. So, what makes you a good designer now is, having understood the theory, you now ask yourself, what is the formula for high pass filter or low pass filter? At this stage, you are no longer you are no longer struggling to understand what a resistor or capacitor is doing in a circuit. You are interested in the specific values now. And then once you generate the formula, you are good to go. When it comes to explanation of the circuit, you explain the circuit and then you attach the mathematics to it, get your values, simulate it. Once it begins to work, you go ahead and build it. That what makes you an expert. Okay. Is there any other
Thank you, sir.
concern? Is there any other concern?